Hello students, Miss Slyman here. I said that I was going to make a video of our most recent Desmos activity, the roles and mean value theorem. So here it is. So this activity starts by showing you a picture of a graph and then asking whether the orange line is secant or tangent to the purple. So I see that it's tangent at this point, x equals 0, but I could also say that it's secant between x equals 0 and this point of intersection here, which is negative 3.8. So I'm going to say that it's both. It's tangent at x equals 0 and secant between the 2 points of intersection. All right, so that's our reminder of what's the difference between a tangent and a secant. And what we're looking for is the relationship between tangent lines and secant lines for a variety of functions. So this is the goal, relationship between tangents and secants. All right, so currently we've got our secant to the function, and then we've got the black line, which is tangent. So the greater slope is the secant line. All right, other people agree with me? Drag the black point until the tangent line is parallel to the secant line. So I want these two lines to be parallel. Looks like it's about there. All right. So I've got my interval on the x-axis between the points of sequency to be a and b. So that means I'm going to call this a and this b. There's my x-axis. And I found my tangent line with my point of tangency between A and B. So is it possible that this can always happen? Can I always find a tangent line between A and B that's going to be parallel to my secant line? So as of now, it seems like it's always possible. But you know me, always going to be tricky. So let's go on and see what happens. All right, so here I have a function. This is a continuous function, and it is a function. For every x, there's only one y. But I want to drag my point of tangency between those 2 points to find a parallel one, but I see that I can't do it. The parallel point would be somewhere out here where it flattens out some more. So that's impossible. And we can't do it because there is no point where the tangent has a matching slope, while this function is continuous. It is not differentiable. So I see that it's not differentiable at x equals 0 because I go from a negative slope to a positive slope at that one point. So no tangent right when x is 0. And I can see that my tangent line disappears when x is 0 because the slope does not exist there. All right, so now I want to do the same thing. I've extended my 2 points, so that's not quite parallel. There we go, maybe there. So this time we could do it. Done. And between points of sequency, the graph is continuous and differentiable. All right, this time I have a function that appears to be constantly differentiable, but it is not continuous. So my guess is that we're not going to be able to do it. And sure enough, we cannot. Nope, not continuous. Okay. So plot a function for which every secant line has a parallel tangent in between points of sequency. Well, I hope you're getting the point that I can just pick any continuous differentiable function. A function for which some secants have parallel tangents and some do not. Well, I'm going to pick a function that's not differentiable, like absolute value of x. It's not differentiable at every point. So is it possible to plot a function for which none of its secant lines have a parallel tangent? I don't know. I'm going to let you think about that one. All right, so necessary conditions must be continuous and differentiable. Continuous. So here's my definition of the mean value theorem. That if I'm continuous and differentiable on an open interval a to b, there's some value in between, so we're going to say c is in between a and b, such that the slope of the tangent line is the same as the slope of the secant. So the slope of the secant will be y minus y over x minus x, and the slope at c is going to be the same. Continuing off of that, we've got one special situation where f of a equals f of b. So for example, I could move that to about there, move this one to about here. So now I see that f of a equals f of b, which is 5. And my slope there, so slope of secant is 0. That means that up here will be my point C, where I also have a slope of 0. So slope of 0, so that leads to a point with a tangent that has a slope of 0, which will be an extrema. So my slope of 0 is going to be up here. That's where I've got my maximum. Similarly, if I had taken my point A, I restricted where A could be. All right, let's see. Can I bring B over here? Nope, I also restricted where B could be. Had I put B over here, though, I would have found this as my point C, and it would have been my minimum. So this extension of mean value theorem is what we called Rolle's theorem. So AP won't explicitly refer to Rolle's theorem, but it will ask you about this extension of mean value theorem, where you would say that it's where your 2 points, your secant points, have a slope of 0 because their y values are the same, which means there will be a point in between them, which is either a maximum or a minimum.